All right, so let's summarize once again, and in the purpose of summarizing here is going to be to help us solve some navigation and velocity vectors. So the results from the previous slide can be summarized as follows. Given the magnitude of a non-zero vector v and the direction angle alpha, where alpha is being defined as being an angle between 0 and 360 degrees, and that angle is between the vector and the horizontal axis, then vector v is defined as the magnitude of the vector times the cosine of the angle times I, which is the unit vector, plus the sine of the angle J. In addition, if a vector represents the speed and direction of an object, we say that it's called a velocity vector. So let's look at this example. A Boeing 737 aircraft maintains a constant airspeed of 600 miles per hour headed due south. The jet stream is 60 miles per hour in the northeasterly direction. So let's just make sure we understand the two pieces of information here. We've got the aircraft with an airspeed of 600 miles per hour, and it's going south. And then we have the jet stream, which is 60 miles per hour, and that's going northeasterly. That's like the wind. Express the velocity v sub a of the 737 relative to the air. So, we could just call it v. The a is to indicate that it's the speed relative to the air. And the velocity v sub w, what do you suppose w stands for? W is the jet stream, so maybe that's the wind you might think of, in terms of both I and J. Now in terms of I and J, don't let that bother you because we have a formula for that right here. I can write vector in terms of I and J if I know something about the angle. I can use the cosine and sine, and if I know something about the magnitude or the length of the vector, which I think I do in both of these cases. So I'm going to start out with v sub a, and I'm going to say that v sub a is equal to the magnitude of that vector, which is 600, that's my speed, times the cosine. Now what's the angle? I'm headed due south, so from the positive x-axis, due south would be a 270-degree angle. And then I throw the I in there, that's how many unit vectors, and then plus also the sine of 270 degrees, J. And if I simplify that, I've got my answer. Now you can put that into your calculator, but let's see, cosine of 270 degrees is 0, so I'm going to get 600 times 0I plus the sine of 270 degrees is -1. And if I simplify, it looks like I get -600J. Now I want you to think about this for a second because I actually think we probably could have come up with this picture without using the formula. If you think about that aircraft going south, right? So let's see, green's not going to work. Let me switch to white. Okay, so here's my axes, right? So I always put it as a position vector. So here's my aircraft taking off, and if it heads south going 600 miles per hour, how would you have described that vector based off of what we learned in the previous slide? Well, in the previous slides, we said that we could write that vector, we could write the component form of that vector by recognizing what is the horizontal movement and what is the vertical movement to get to the terminal side of that vector. So I'd be going nowhere on the horizontal axis, and I'd be going down 600 units. So that's why the I piece goes away, and we're left with just -600J. Anytime you're right on an axis, you can do something like that. It's when we get into diagonals that it might be a little bit harder to visualize. And maybe, I think we see that on the jet stream. So let me go ahead and look at that one. V sub W is going to equal, let's see, the magnitude of my jet stream is the 60 miles per hour. So 60 times the cosine. Now what's my angle? I'm going north, but a little bit east. So with the positive x-axis, it looks like that's a 45-degree angle. And that's good that we know something about 45-degree angles. Plus the sine is going to be the same thing. And if I simplify this, I think I get, well, 45 degrees, I'm going to get root 2 over 2. So 60 times root 2 over 2i plus root 2 over 2j. And if I simplify that, I get 30 root 2i plus 30 root 2j. Now, that's a great answer. If you want, you can get a decimal approximation to that problem. And I think we're going to continue this on the next slide. So I'll go ahead and put the decimal approximation on the next page. All right, so here's the original problem, and on part A, I put in orange there the answers that we got from the previous page, and I told you that I would write the decimal approximation for the airspeed. Now I'm going to put that on there just so we have a vision of what quadrant we're in. 30 times the square root of 2 is around 42.4, and let's see, 30 times, I guess it's the same thing, isn't it? 42.4 J. All right, so I want you to imagine what's going on here. I have a plane. That is wanting to fly south, but there's a wind that is blowing this direction. Okay, so what do you think is going to be the effect of the location of this plane? And that's what we're going to talk about on part B. Part B says find the velocity of the 737 relative to the ground where the following is true. Airspeed, which we know, or at least have a position vector for it, and wind speed, which we also know something about, is equal to ground speed, and they want me to find a velocity vector for ground speed. So I'm going to call that vector ground speed, I'm going to call it V sub G. Okay? All right, so what they told me is that V sub G is V sub A plus V sub W. All right, and let's see, V sub A, I was told, is negative 600 J, and V sub W is 30 root 2I plus 30 root 2J. And just like when you added in algebra, when you first learned how to add, you can only add like components. So I'm going to go ahead and move the 30 root 2I up to the front because we usually see I written first. And then for the J's, I'm going to write plus negative 600 plus 30 root 2J. And I wrote it like that because I can't directly add 30 root 2 and negative 600. To get a little bit better feel for it, this is where I'm going to put this into my calculator, and I get 42.4i. And if I take negative 600 and I add 30 root 2 to it, I get negative 557.6 J. So this is what's happening to the plane. Okay, so the plane started out going south, and then the wind picked up, and how did the plane's position change? Well, it was, remember what it was? It was this one, right? So it was going nowhere on the horizontal axis and going down 600. Now, if you go over here, if you go up to the top and look at my graph, now I'm actually moving a little bit to the right and not down quite as far. So it looks like my plane has been moved a bit east because of that wind. We've got another question to ask on the next slide. Let's see if we can get this one. All right, one more part to all of this. And there was our part A that we came up with, and there's our part B that we came up with. And now here's the question for C. Find the actual speed and direction of the 737 relative to the ground, where again, we already know that the following is true, that the actual speed is equal to the magnitude of the ground speed. So they're actually asking us to find the actual speed, and then I tell you that the actual speed is the magnitude of ground speed. Well, what's ground speed? Ground speed is what you found up on part B, right? That's ground speed. That's my component form of ground speed. So what I need to do is find the magnitude of that. In other words, I need to find the length of it. Now, do you remember how to find the length? In other words, what I'm talking about is taking my ground speed vector and finding its magnitude. If you go back a couple of slides, you'll see that the formula for this is just the Pythagorean theorem. That's what's so nice about writing things in component form, is that you form right triangles. So it's going to be a little bit ugly because the piece connected to the I is 30 root 2. I'm going to square that, plus the piece connected to the J is negative 600 plus 30 root 2. Now you might be asking yourself, well, could we just use the decimal approximation that we did on the last slide? What was that? 42.4 I and plus negative 557.6 J. Well, I hope you know the answer to this without me even saying it, but I'll go ahead and say it just in case it's not clear. You could use that and you'd probably get pretty close, but because there's rounding that went on with that decimal approximation, there's a potential that your answer is going to be off a little bit. So if you want to make sure that you get the absolute as accurate answer as possible, you've got a calculator, so you should be able to input all that into your calculator. So I would always suggest that you use the exact numbers. So if I put all that into my calculator, I got 559.19. That is the actual speed if I consider what's happening with the wind. Now, if you recall, what the plane was actually wanting to do was 600 miles per hour. So what did the wind do? It slowed it down. That's why sometimes if you're on a plane, you might get there faster or you might get there slower, depending on whether or not the plane is traveling with the wind or against the wind. Now that's what we call the actual speed. The other part that they want to know is the direction. In other words, what is theta? Well, what we know, if you recall, what we know is that this 30 root 2 is a horizontal movement. It's like an X. And the negative 600 plus 30 root 2 is our vertical movement. It's like a Y. And so if I'm interested in finding an angle, and I know X movement and I know Y movement, in other words, I don't know the hypotenuse. Well, I actually do now, but I'm going to use the answers that I got before, or the earlier answers. And I do have a right triangle. I can use my SOHCAHTOA rules. So I'm going to use tangent of theta, and I'm going to set that equal to my y over my x. And don't be afraid of this, because again, you've got a calculator. So you've got negative 600 plus 30 root 2 as your numerator, and you have 30 root 2 as your denominator. So you're going to put all of this into your calculator. Theta is going to be tangent inverse of, whoop, my pen's bothering me here a little bit, is going to be tangent inverse of all of that. And when I put that into my calculator, I got negative 85.65 degrees. Now, we always want to write direction with a bearing. And so if you think about a theta of negative 85.65 degrees, let's just draw a little teeny graph here in the middle. You would be starting on the positive x-axis and then going clockwise negative 85 degrees. As a bearing, remember how bearings work. Bearings work by you always giving the north and south directions first. So what we could say is that this plane is going south and then it's going a little bit east. Now, how east is it going? Well, the amount of east that it's going is whatever that angle is. And because the entire quadrant is 90 degrees, if I take 90 degrees and I subtract out the 85.65 degrees, I think I've got my answer. So I end up with a direction of south. I got 4.35 degrees and east. All right, now let's try an example where all of the parts that we've done so far are being combined into one. So this is a big one. An airplane has an airspeed of 600 kilometers an hour bearing south 30 degrees east. The wind velocity is 40 kilometers an hour in the direction south 45 degrees east. Find the resultant vector representing the path of the plane relative to the ground. In other words, after the wind has had its effect. And then what is the ground speed of the plane and what is its direction? So the direction will be finding theta. The vector representing the path relative to the ground will be like us just writing a v sub g, using the pieces from airspeed and wind. And then ground speed will be the magnitude of that vector that we found. Okay? So before we can find v sub g, we need to find v sub a, and we need to find v sub w. All right, so let's see here. Go back a couple slides if you have forgotten, but we're going to start with the speed of the plane, so that's 600. And I'm going to multiply that by the cosine. Now this is a bearing of south 30 degrees east. Now let me just show you something here. If I sketch this out, if I go south and then 30 degrees east, I end up about right here. So if I say 30 degrees, is that going to give me an answer that is representative of a theta between 0 and 360 degrees? And the answer is no, because we're always working off of the positive x-axis. So this is where it gets a little bit tricky, because you actually have to visualize where you end up at. So really it's going to be all the way past into the fourth quadrant. So 270 degrees plus 30 degrees, it looks like that's going to be a 300 degree angle. Now that's based off of the definition of theta being between 0 and 360 degrees. If you wanted to write that as a negative angle, technically you could get away with it, but I'm going to follow the definition that was on the previous slide, and that will, for consistency's sake, always get you the right answer. So I'm going to use 300 degrees, and I'm going to use that for my sine, and I'm going to use that for my cosine. And if I simplify that down, let me see, what did I end up getting? Cosine of 300 degrees. Let me just go ahead and give you the answer that I got, and you make sure you verify that you got the same thing. I got 300I plus negative 300 root 3j. Okay? And then for the wind, let's take a look at the wind. The wind has a velocity of 40, so I'm going to say 40 here, times the cosine. Now it says 45 degrees south and then east. So the same thing is going to be true for this one. If I draw a picture of that, 45 degrees, this is 45 right here. In order to write this from the positive x-axis, I need to find out what that angle is. So that's going to be 270 plus 45, so 315 degrees. Now you don't always have to do this, because sometimes, you know, if I was in the first quadrant, if this was headed northeast, then I'd be in the first quadrant and I could actually use the 45. It's because of the quadrant that I end up with in heading south first. Okay, and so I'll let you do the simplification on this one. Verify that you get the same as me, 20 root 2I plus negative 20 root 2 and j. And so the velocity vector for ground speed is simply the sum. It's the sum of this vector for airspeed and this vector for wind speed. And so I'm going to go ahead and just combine the i's together. That's going to give me 300 plus 20 root 2I plus negative 300 root 3 plus negative 20 root 2 J. I think that looks right. And I always like to just get a feel for that, so I plug it into my calculator just so I can sort of get a feel for whether or not this answer feels like a good one. And I'll show you what I mean by that here in just one second. So 300 plus 20 root 2 is around 328.3I plus my J component is going to be negative 547.9. Okay, so let's think about this for a second. Looking up at my sketches at the top, if you remember, my first sketch was what I intended to have my plane do. And then we had some wind that came through and affected it. So now, instead of, let's see, my airspeed was going 300 this direction and then going down negative 300 root 3. Now the wind, it looks like this wind is pushing me along because I'm not going 300 anymore. I'm going about 328. So I'm actually going this way, and then I'm actually, instead of going down negative 300 root 3, I'm going down further. So, you know, I don't have the angle yet, but I feel as though that answer makes sense. So that's why I do the decimal approximation. If I got something that had both negative pieces, I doubt that, unless it's a very strong wind, but I doubt that a plane that was headed southeast is going to end up going, say, northwest. So I feel pretty good about that. So what is the ground speed of the plane? This is the velocity vector. To get the ground speed, I now need to find the magnitude. And so do you remember how to find the magnitude? That's where we use the Pythagorean theorem. So I'm going to take my 300 plus 20 root 2 squared, and that is the I component of my ground speed vector. And yes, I could put 328.3 and square it. That would get me pretty close. And then plus, I'm going to put, I don't think I can fit it all in, so maybe I can. I'll try it. I'm going to put negative 300 root 3 minus 20 root 2 squared. Now, aren't you glad we have a calculator? This is exactly where we're going to actually use our calculator for the final answer. So it's fine to round, but you don't want to round until the very end. So if I put all of that into my calculator, I got approximately 638.7 kilometers an hour. So I started out going 600 kilometers an hour, and what did the wind do? Well, the wind was going in the same direction, so it actually pushed me along and it made me go faster. And then the final part is to find what is the direction. And so I'm going to do tangent theta of my y value, which was negative 300 root 3 minus 20 root 2 all over 300 plus 20 root 2. And if I take tangent inverse of that, I got negative 59.07 degrees. Remember, my calculator is always going to spit out an answer for tangent that's between pi over 2 and negative pi over 2, or in this case, 90 degrees and negative 90 degrees. We want to write this as a bearing. So if I'm headed, let me just do one more little sketch for you up at the top. If I am going negative 59 degrees, then as a bearing, I'm headed south and then something east. And that something east is whatever 90 minus 59.07 is. And when I put that into my calculator, I got 30.9 degrees, rounded to 1 decimal place. All right, so ground speed of the plane is 638.7 kilometers per hour. That's my airspeed with the wind affecting me. And the angle is now south 30.9 degrees east. So you can see that from where I started going 30, my angle has been pushed a little bit more east. So I think that that makes sense. So the previous two examples have allowed us to solve word problems using the idea of components and vectors. In example 8, the question is, how could you have solved example 6 using the law of sines and cosines? So remember what that problem said. You can go back to that example, but we had a Boeing 737. It maintained a constant airspeed of 600 miles per hour, headed due south, and I've got a picture of that. In other words, what they told us was that the airspeed was 600 miles per hour headed due south. And so the vector in blue that you see is having a length that is 600. And we said that that was an angle of 270 degrees with the positive x-axis. Now, if we're going to talk about law of sine and cosine, then what we're really going to be paying attention to is how can we make triangles out of all of this. The second piece of information on that problem was about the jet stream, or in other words, the wind speed. And we were told that the jet stream is 60 miles per hour in the northeasterly direction, and we were to assume that that meant a 45-degree angle. So the wind speed vector that you see in green up at the top had a length of 60. All right, the question was to find the ground speed. The ultimate question was to find the actual speed and the direction of the ground speed. So we're going to take a look at this from the perspective of how do we add vectors. And on one of the first slides, I talked about the fact that if you want to add vectors, which is really what we want to do here, we want to take airspeed and we want to add it to wind speed. In fact, that's what we did when we worked with components. But if I can think of this in terms of adding physical vectors on the graph, then what I know is if I want to take airspeed plus wind speed, I need to connect the terminal point of airspeed down at 0, negative 600. I need to connect that terminal point to the initial point of wind speed. So what I've already done for us is I've taken that original vector of wind speed and I've just moved it down so that it connects to the terminal point of airspeed. So what I had up in the first quadrant, now I'm going to call wind speed 1, still has a length of 60. But now what this does for us is it allows us to write the sum of those two vectors as ground speed. And ground speed is going to be the vector that connects the two of them. And when we connect, we see that we have formed a triangle. Now it's not a right triangle, so that's why we can't use the SOHCAHTOA rules. So let's see what we've got here. We have two sides, and do we know any angles? Well, the angle that we do know is that 45-degree angle. In fact, when wind speed took off, we were told that it was headed in a northeasterly direction, and that northeasterly meant 45 degrees. So originally we had a 45-degree angle up in the first quadrant. Now that 45-degree angle is down in the fourth quadrant. All right, so what I see that I have here is a side and an angle and a side. And when you know something about side, angle, side, then that tells me that I'm going to use the law of cosines. And the side that I want to solve for is ground speed. I think I'll call that x. So I'm going to say that x to the second power is equal to the length of the two sides squared, so 600 squared, plus 60 squared minus 2 times 600 times 60 times the cosine of 45 degrees. Now, one thing that you may be thinking about is, why am I not using negative 600? And let me just address that for a second. Even though we had to go down 600 to get to that value, when we talk about law of cosines, we're talking about the length of that side. And the length of that side is the absolute value, so it's actually positive 600. All right, so I'm going to let you put all of that into your calculator, and when you square root it, I hope that you end up with the same answer that we got on the previous slide, which was approximately 559 point, I think I said 19 miles per hour. So that's the length of that vector. And then the other thing that we can find is the direction. So if I let theta be the angle that's inside that triangle, now that I know what the ground speed is, I can say that the sine of 45 degrees over 559.19 is equal to the sine of theta over the side across from it, which is 60. I'm going to multiply both sides by 60, and when I put that into my calculator, I get a theta that is equal to 4.35. And because that 4.35 degrees is bordering a vertical distance, in other words, it's headed south, unlike what I had to do when I was working with components, this gives me the direct answer. I can say that my aircraft is going south 4.35 degrees and a little bit east. So that's good news. You might want to go back and forth between the two ways that we did this problem and decide for yourself which way that you like best. In some instances, I like using law of sine and cosine better. It's easier for me to see. In other cases, I like using components. On this one, I think I liked using the law of sine and cosine that I see in this picture. It was really easy for me to see the triangle. But let's take a look at the next example, and I think you're going to see it's a little bit more difficult to see the triangle. All right, so here's example 9. Now we're going to go back to example 7, and I'm going to show you the picture. I graphed these in GeoGebra, and you can see this one's a little bit harder to see just because the angle is so tight in there. We have an airplane that has an airspeed of 600 kilometers per hour with a bearing of south 30 degrees east. So let me see here. In blue, I've tried to color code these a little bit for us. In blue, we have the airspeed, and so that is, let me go ahead and write it in blue, that's going to be 600. And let's see, what else do we know? They said that I was going south 30 degrees east. So this angle right here is 30 degrees. Now, what do we know about wind speed? This one said the wind velocity is 40 kilometers an hour in the direction of south 45 degrees east. So the wind speed vector that's up here has a length of 40 and it has a 45-degree angle involved. So what I'm going to do in order to see the triangle is I'm going to pick up that wind speed vector and I'm going to connect its initial side to the terminal, its initial point to the terminal point of the airspeed vector. And you can see that that wind speed vector just moved all the way down here. All right, so this side here is 40. Now here's one of the tricky parts, is trying to figure out what is this angle that's in between. And it's a little bit hard until you've got to think about where did all of these angles come from. And I'm just going to go up here and sort of show you the way that I think about this if I was drawing it by hand. If I was drawing this by hand, I'm going to see if I can make this look a little bit better. I would have started out going south and then the 30 degrees east. So it would have looked something like this. Okay, there's my 30 degrees. And then at that point, it says I would have added to that a vector going south 45. Now you've seen us do this before. I make another axis on here, and that wind is going to be in the direction where this is a 45-degree angle. Now I think that that helps a lot, because now I can see that the angle that I'm interested in is comprised of this angle, a 90-degree angle, and a 45-degree angle. So if I can figure out the angle that I've circled, I think all I have to do to find that angle in the inside is take 90 plus 45 and whatever that angle is. Well, there's triangles all over the place. If I were to extend this all the way up, I would see another triangle. And if the angle here is 30 degrees, then this one must be 60 degrees, which makes this angle 30 degrees. So it looks to me like my angle on the inside is whatever 30 degrees plus 90 degrees plus 45 degrees is. And I came up with 165 degrees. So in order to find ground speed, I'm going to call ground speed x, and I'm going to say that x to the second is equal to 600 to the second plus 40 to the second minus 2 times 600 times 40 times the cosine of 165 degrees. And when you put that all into your calculator and you take the square root, I hope you get the same answer that we got, which was approximately 638.7 kilometers per hour. All right, and now I want to find the bearing. And so it's really hard on this GeoGebra picture, but because it's so small, what I need is probably to consider what is this little teeny angle that we can't even see, but that's in between there. And so maybe if I open this up a little bit, what we have is this triangle, and inside that triangle, we know that we have a 165-degree angle. We also know that the angle that I'm interested in is across from the side that has a length of 40. So let me do this. Let me call that angle, that little teeny one, theta. So this is theta. I'm going to say that the sine of theta over 40 is equal to, and now I'm going to say the sine of 165 degrees over the 638.7. So if I multiply both sides by 40 and I take the inverse sine, I end up with, let's see, I got something really small, 0.93 degrees, I think. But we have to remember that we want bearing, and bearing is always directed either north or south. So my plane is going to be headed south. It's going to be 30 degrees plus that little teeny part of 0.93 degrees. So I'm going to say that my plane is headed south 30.9 degrees. I could say 0.93, but usually angles we round to 1 decimal place, and then a little bit east. So it looks like it's the same answer that we saw on the previous slide. So you decide which one of these methods do you like better. Do you like what we did in the beginning where we did components, or do you like drawing the picture with the triangle and using law of sine and cosine? Either way works fine with me.